Hi everyone. In this lecture, we will discuss about the response of LTI systems to sinusoidal inputs. So assume that we have an LTI system with a transfer function given by h of s and an impulse response h of t. And we are feeding an exponential input of this form, which is e power s naught of t. The output of this system is given by the input, which is e power s naught of t multiplied by h of s naught, where h of s naught is nothing but the Laplace transform h of s evaluated at s equal to s naught. I'll actually give a more rigorous proof of this result when we start discussing probably in the next lecture. But right now, I'll only quote the final result and try to draw some intuitions out of it. So we have the final result, which is the output y of t is given by the input, which is e power s naught of t multiplied by h of s naught, which is the Laplace transform evaluated at the Laplace transform of the impulse response, which is your transfer function evaluated at s equal to s naught. Now if I substitute s equal to j omega naught, so that will be a sinusoidal input of this form, x of t equals e power j omega naught t, where e power j omega naught t is actually a complex sinusoid. So then h of s naught would become h of j omega naught. So that's nothing but your transfer function h of s evaluated on the j omega axis. Okay. So then your output is simply, this output is a complex output because your input is a complex input. E power j omega naught is a complex input. So if I want to take the real part of it, if I take the real part of e power j omega naught, I'll get cos, which is a real sinusoid. So for a real sinusoid, I can just take the real part of this expression. So that will be real part of, I'll assume that the amplitude of the sine wave is Vp. So you'll get Vp e power j omega naught of t into h of j omega naught. Okay. This is nothing but, if you see, h of j omega naught is nothing but a complex number. So it's a complex number, so it will have a magnitude and a phase component. Okay, it can be written as in a polar form this way. So the magnitude will be multiplying the magnitude of the input, and the phase part will be adding to the phase of the input. So finally, for a real sinusoid of frequency omega naught and zero phase, the output is given by this. So the first term, the magnitude is going to be multiplied by the magnitude of the frequency response evaluated at omega naught, and the phase is going to be determined by the phase of the frequency response at omega naught. So this is something we are already aware of. This is what we call the sinusoidal response of a LTI system. So what does this result tell us? It tells a very important result. It's a very important consequence is that if the input frequency is omega naught, the output frequency will also be the same. Okay, the output frequency will also be omega naught. Okay, and the other important thing, this is true for a linear time invariant system. Your output cannot have frequencies that's not present at the input. The other thing is that if h of j omega naught is infinity at any point, so if there are any singularities on h of j omega naught, then the output will grow unbounded for a bounded sinusoidal input. So even if you apply a sinusoidal input of finite amplitude V peak at frequency omega naught, if there is a singularity at that point, at singularity meaning if there is a pole, that's the term we were using, where your transfer function or the frequency response blows up to infinity, then your output will also be blowing up to infinity. Okay, it will grow unbounded. So here I've shown this three standard transfer functions containing real poles. The first one is a pole at s equal to 0. So here if you see, when you actually try to evaluate this along the j omega axis, the frequency response itself has a discontinuity at s equal to 0. So yes, then for some sinusoid, this can give you an infinite output because the transfer function itself offers an infinite gain, so you can expect an infinite output. And shown here is the frequency response for a left of plane pole and the frequency response for a right of plane pole. Now if you see, interestingly, the magnitude response is the same whether it's a left of plane pole or a right of plane pole. So therefore, you should expect similar amplitudes. When you feed a sine wave, I should expect a similar amplitudes from both the transfer functions. The phase will be different, okay, but amplitudes will be similar. We will later see it is only partially true, and the outputs can actually become unbounded if you have right of plane poles, and that's something we are already aware of, and we'll see where does this difference come from. But if you look at this expression, which is the expression shown here, okay, this doesn't show that. I mean, whether it's a right of plane pole or a left of plane pole, you are supposed to get a bounded output. Okay, by this definition, we have to get a bounded output, right? Your h of j omega is bounded for both the left of plane pole or right of plane pole. H of j omega is bounded, so therefore output is also should be bounded. The other case is when you have complex poles. So again, whether you have right of complex poles or left of plane complex poles, on the j omega axis there will be no singularity. Okay, your j omega, I mean, when you find the frequency response, it's never going to blow up to infinity at any frequency. So which means if I apply any sinusoid, the output as per the equation that we have discussed should be bounded. Okay, and in this case here we actually have poles on the j omega axis itself. In that case, if I feed a sine wave of frequency omega naught to this system, you should expect the output to grow unbounded. So now we will do the analysis of all these different kinds of systems by feeding sinusoids and see what happens to them. So to quickly summarize, we just discussed that if you know the frequency response, h of j omega naught, then you can predict the output for any sinusoid. The amplitude of the sinusoid gets multiplied by the value of the frequency response at that frequency, and the phase also gets added by the phase of the frequency response. Okay, measured at that frequency, of course. But there is a small difference here. This result which we have derived, it is assuming that your input cos omega naught t has been an everlasting sinusoid, meaning it, for example, normally when you perform an experiment, you start an experiment at some point. Okay, so we'll assume that as t equal to 0. So if I just write cos omega naught t, mathematically it assumes that the input has been existing for a very long time. Okay, and there will be a the input is going to be continuous at t equal to 0. But that's seldom the case. I mean, normally, in fact, it's never the case. So for example, you may be taking a signal out of a function generator and feeding it to a circuit. Okay, so usually when you kickstart an experiment, there will be a sudden change in the input. So you will have a discontinuity at the output and in the input itself. So it is input of this form, which is x of t equal to 0 for t less than 0. So these are the kind of inputs we'll be feeding to practical systems. So the inputs will be of this form, cos omega naught of t into u of t. Now we'll see what happens when you feed an input of this type, and we'll try to intuitively analyze what will be the outputs for different transfer functions. So first I'll assume a left of plane pole, okay, so which is simply a simple first order RC circuit shown here. So the frequency response is given by 1 by 1 plus j omega RC. Transfer function is 1 by 1 plus SRC. Okay, and I'm going to call omega p here as 1 by RC. Okay, it's a left of plane pole system. Now our goal is to find, I'm going to feed an input of this type, Vp cos omega naught t into u of t. What will be the output for this system? Okay, if it was just Vp cos omega naught t, we already know what the output is. Okay, we can just use this equation to find the output. But then there is a u of t multiplying this, and that makes all the difference. I'll give a more rigorous proof of this in the next lecture, as I already discussed now, as I already told you now. Okay, so in this lecture we'll try to stick with some results that we are aware of already, and then we'll try to draw intuitions based on that. So to solve this problem, I'll solve a problem which we are well aware of, which is I'll take the special case when your omega naught tends to 0. If your omega naught is 0, then for any value of time, cos omega naught of t will be 1 always. So then this cosine, the sinusoid, reduces to a 0 frequency sinusoid. That's nothing but a step function. Now we know if I feed a step input to an RC circuit, it's going to be, eventually the capacitor will behave like an open circuit, and this entire voltage will appear at the output and all that. So we know that it's going to be a first order response, and asymptotically the output is going to reach the output is going to reach the input. So the output is actually going to be of this form, Vp into 1 minus e power t by tau into u of t. Okay, so it's going to exponentially rise, but eventually it's going to reach, it will never exceed the input. So I'm going to rewrite this result, split this result into two factors. One, I'll write Vp into u of t, which is nothing but your input. And then there is other term which is Vp e power minus omega t into u of t. So the first term is what we call as the forced or steady state response. The second term is what we call the natural response. See, whenever you apply a sudden change to the system, your system is going to respond to that. So when you, for example, impulse is like a sudden change, you're just suddenly giving an input to the system and then taking the input away. You're just making it zero again. And the response of the system is what we call as a natural response. So whenever there is a sudden change, when there is a discontinuity in the input, okay, the system will exhibit a natural response to that, in addition to the forced response, which is due to the input itself. So we'll see the forced response term, which is nothing but Vp into u of t, which is same as the input. And that should make sense because if you see it's an input can be seen as a sinusoid of zero frequency. And we can see from this equation h of 0 is equal to 1. So therefore, the output is simply Vp into h of 0 into u of t, which is Vp into u of t itself. The second term is what we call the natural response, and that is determined by the impulse response of the system. Okay, that again is determined by the poles of the system. Okay, so this term eventually in the steady state, what will happen in the steady state is that this term is going to die down. If a system is stable, meaning if all the poles are in the left of place plane, then this term is eventually going to go to 0. This term here will go to 0. Then you will be only left with the forced response. Okay, and this is what we have discussed in the beginning of the lecture, how to find the forced response. But this is not something we didn't figure in before. So extending this result, I am now going to apply it for a sinusoid as well. So here the input is Vp cos omega naught t. In that case, I'll have a steady state or a forced response, which will be estimated using our frequency response analysis, which is the peak amplitude Vp dash is given by Vp into mod of h of omega naught. And the phase again is determined from the phase of the frequency response. In addition to that, there will also be a natural response term. That will be determined by the poles. So here alpha is a constant here. Okay, I assume this. In the steady state, what happens is this term will go to 0. This term will go to 0. You will have only this term left. So that's why this is the steady state response. What we discussed a few moments ago is actually only the steady state response. So I've shown here in this graph both the input and the output. Here I've shown the amplitudes to be the same, but they will not be that will not be the case. So here for the red curve, that's your output. Your V peak, the peak value should be Vp into mod of h of j omega naught. And then if you see there is a phase difference between the two waveforms. That phase difference phi will be your phase of the transfer function measured at omega naught. Okay, so that's the only difference here, and we have shown what I've shown here is actually the steady state response for a left of plane pole system to a sinusoidal input. Now we will analyze the same sinusoidal input being fed to a right of plane pole system. Here the right of plane pole is on the right of plane, and the location is same as the left of plane. The magnitude is same. Okay, instead of minus omega p, the pole is now at plus omega p. Now in a similar way, I'll write the expression as Vp dash cos omega naught t. So this is your steady state or forced response, and this part is your natural response, some alpha times e power plus omega naught t, plus omega pt, sorry. Okay. Now if you look at the transfer function, the first term is pretty simple. I mean, it's going to look the same as it was for a left of plane pole. The left of plane pole, it was Vp dash cos of omega naught t plus phi of omega naught. The only difference is in the phase. Okay, this is going to be an advanced version. This is a delayed version. You can see that from the transfer functions itself. I'll not go into that now. We are just looking at the intuitions. So this function, the only difference is the amplitudes are same, frequencies are same. The only difference is in the phase. Okay. The other difference is, the big difference occurs in the natural response. The natural response term is eventually an exponentially growing signal. It will eventually grow, unbounded, and it would eventually go to infinity. So that's the difference here. In the steady state, this would dominate because it's an exponentially growing output, and this is always, it's going to oscillate back and forth between Vp dash. Okay, so this is going to determine the fate of the system. I mean, the system is eventually going to go to infinity. The output will go to infinity. So that's why this is an unstable system. So even if you feed, see, the analysis that we did some time ago, we said that if you fed a sine wave, whether it's a left of plane pole system or a right of plane pole system, if you just blindly, if you just go by the frequency response analysis, then you will only get the first term, and that's a stable output. But then when you apply, because there is a sudden input, you are applying the input suddenly, whenever there is a sudden change, then your system will exhibit a natural response. And that natural response for a right of plane pole system is unbounded. So therefore, if you feed a sine wave to a right of plane pole system, you should expect an unbounded output. The output in fact will look like this. So there is a sine wave here riding on top of an exponentially increasing signal. So this is the output for this system. Okay. So what we have discussed so far is, we have discussed system with left of plane and right of plane pole, and we said that ideally we were expecting similar responses if I feed a sine wave to both these systems, but then we just saw that right of plane pole system, the natural response is going to make the output to grow unbounded. Okay, whereas for the left of plane pole system, which is a stable system, we can directly use the frequency response analysis to predict the output in the steady state, because all the contribution from the poles or the contribution, the natural response is eventually going to decay down to zero, so it won't matter in the steady state. But for right of plane pole, the natural response is just going to grow unbounded, so that's going to dictate the fate of the system. Now the next case, we'll analyze pole at origin. So we have so far analyzed the left of plane and right of plane. So now we'll analyze pole at s equal to 0. Our goal is to now find what happens when you feed an input Vp cos omega naught t into u of t to the system. I'll again go by a similar way. There will be a forced response which is found using the frequency response method. You just have to multiply by the magnitude of the frequency response. I fed a signal cos omega naught t. Output is going to be sine because the transfer function is 1 by j omega naught. The frequency response is 1 by j omega naught. So the phase is minus pi by 2 for this. Okay. So if you fed a cos, you are going to get sine as an output. And then the natural response here is nothing but some scaled version of the impulse response is u of t, is a step function. And that should make sense because 1 by s is an integrator. If I feed an impulse to the system, it's going to integrate an impulse. That will be nothing but a step. Now if you see, if your frequency omega naught is finite, this term is going to be finite, and this is also finite, so which means the output is bounded. So you apply any sinusoid, any non-zero frequency sinusoid, you are going to get a bounded output. Of course, the gain can be large for lower frequencies, but still a bounded output. But what happens at omega equal to 0? At omega equal to 0, we can see from here the forced response itself tends to infinity. The natural response is finite, it's not blowing up, but the forced response is actually blowing up to infinity. So when omega naught tends to 0, that's nothing but a zero frequency sine wave, cosine. So that will be just a step function, Vp into u of t. So if I feed a step function to this system, we can easily guess that. So it will be integral of a step, which will be a ramp function given by Vp into t into u of t. So the output is unbounded. So here we learned an interesting point, is that for some inputs the system is stable, and for some inputs the system is becoming unstable. So that's why it's a marginally stable system. So here we can see that the frequency response contains singularity on the j omega axis itself. So which means for some inputs it can give you an unbounded output, and that happens to be omega equal to 0, or that is a zero frequency sinusoid, in this case a step input. Okay. So far we have discussed our left of plane pole system, a right of plane pole system, and a system with pole at s equal to 0. So now we will actually go to systems with poles on the j omega axis itself. So these are what we will call for this lecture as resonant systems. So their poles are of this type, s equal to plus minus j omega naught. Okay, purely imaginary poles located on the j omega axis. So to analyze this, I'll take a circuit, a parallel LC circuit, the transfer function will be given by SL by 1 plus S square LC, which is what I've shown here. So I've shown here the transfer functions. Now if you have studied basics of LC circuits, I'll probably give a link in the description box. You can go through some of my lectures in the which I posted last year on how to analyze LC circuits. So again, if you're already aware of it, well and good. So let's say we have an initial voltage V0 across the capacitor, then the energy across the capacitor is going to switch back and forth between the inductor and capacitor. Okay, so the capacitor voltage in the first half cycle will go from plus V0 to minus V0. Okay, at this point, in fact, in 1/4 of a cycle, the capacitor voltage will go to 0. At that point, all the energy will be stored in the inductor as current. The inductor current will be at a peak value. Then the capacitor voltage will go to negative of its. The inductor current will now start charging the capacitor in the opposite direction. So you will get a negative voltage of minus V0. And the voltage, it will be a sinusoidal signal oscillating between plus and minus V0. Okay, so this is how a simple parallel LC system works. Now, instead of analyzing a sinusoidal input, feeding a sinusoidal input and analyzing it, I'll analyze it using feeding a pulse train. I'm going to feed a pulse train. Okay, a train of pulses operate. The pulse frequency is at the time period is t, which is 2 pi by omega naught. All I'm doing is I'm just feeding an input which has an energy frequency component at omega naught. Okay, so if you approximate this pulse train to narrow pulses, impulses, then I can say that the Fourier transform will contain energy at all harmonics of omega naught, 2 omega naught, 3 omega naught, and so on. Now this is a current pulse, so the area under the current will be charge. So I'll assume the charge that each current pulse delivers is Q. So now the instant you are delivering charge to this circuit, the capacitor will offer a very low impedance. Suddenly, for sudden changes, capacitor behaves like a short circuit. So it will absorb all the charge and it will develop a step voltage of value V0. Okay, and that V0 is given by Q by C. So that's what I've shown here. Now what would happen? We would expect it to behave like a sinusoidal oscillator. So it will complete one full cycle. At the end of the first cycle, the current is now delivering another packet of charge of the same value Q. See, at the end of the first cycle, the charge is now, initially the capacitor had all the energy. At this point, the inductor is now storing all the energy which it had borrowed from the capacitor. And at the end of the first cycle, the energy is returned back to the capacitor. All the charge is returned back to the capacitor. At that point, the current source is going to dump an excess charge of value Q by C. So the voltage across the capacitor is going to double. It's going to become 2Q by C. Again, it's going to oscillate for one full cycle here. At the end of the second cycle, the current source is again going to dump a charge of Q by C. The amplitude is going to become 3Q by C, and so on. So now if you see, the amplitude is growing linearly. So as t tends to infinity, this current source would have delivered infinite amount of charge, so the amplitude will also become infinity. So for here we are applying a bounded input. The input is always bounded. Okay, it's a periodic signal with a bounded amplitude. Okay, so input is bounded, but the output is growing unbounded. Okay, that's because the system has a pole at omega naught. It has a singularity. The frequency response itself has a singularity at omega naught. I fed an input of frequency omega naught to this system, and I should expect the output to blow up to infinity. And here, what we are seeing here is that it blows up, it increases linearly. The output actually increases linearly. So there is probably in the later lectures I'll discuss this. This actually behaves like an integrator around omega naught. So which is why it will behave like it's going to have a linear increase the way we saw for an integrator at DC. Okay, so I'll not go into that, but I just mentioned that point. We'll talk about it at a later stage. So all we showed here is that if I feed a sinusoid of frequency omega naught, which happens to be the pole for the system, the output is going to grow unbounded, and that its amplitude is going to grow to infinity. So if you use the exact expressions from the frequency response analysis, you don't really see how it's actually going to grow. Okay, so that's why I showed it using pulses. In fact, if you feed a sinusoid of frequency omega naught of this form, you will actually get an expression of this form. I think it can be cos or sine. Okay, And again, the video that I've posted in the description contains an exact derivation for this result. You can go through that. So all we have showed here is that the amplitude is going to increase linearly, and in the steady state, this is going to blow up to infinity. I'll take another example of a sine wave, because if you see, a sine wave is a signal, it's both positive and negative, right? So I've just considered a unipolar pulse signal, which is always positive. So what I'll do is, if you see a sine wave current source, in the positive half cycle, it is delivering a positive charge. In the negative half cycle, it is removing charge or giving a negative charge to the system. So to model that, I'll lump all this positive charge together. This area, let's say it's Q under this positive half cycle, I'll model it by a very narrow pulse Q. And then I'll lump all the charge in the negative half cycle and model it as a very narrow pulse with a charge minus Q. Okay, so now the time period is same, it's 0 to t is the time period, but the only difference is at one half of the cycle you are going to deliver a negative charge of value minus Q. Now, how do we analyze this? At the positive half cycle, when the first cycle, the capacitor gets a charge of Q by C. So it's going to oscillate for one half cycle. And at the end of one half cycle, the capacitor voltage is going to be minus Q by C. It's going to store a charge of minus Q. At that point, you are going to deliver a charge of minus Q to the system. So the net charge is going to become minus Q plus minus Q. It will be minus 2Q. And the voltage is going to become minus 2Q by C. So you will see a sudden jump in the voltage in one half of the cycle, at the end of the first half of the cycle. Then you will see a similar oscillation for one more half, and at the end of the first cycle, you are again going to dump a positive charge. So that's what I've shown here. Okay, so you're beginning here, delivering the first packet of charge. At this point, you're delivering a negative packet, so it actually assists. It's actually assisting in increasing the energy, so it's actually increasing it further. Amplitude is increasing, and at this point again you are injecting a positive charge, a negative charge at this point, so again the amplitude is going to grow linearly. So if you recall, in the previous lecture I discussed, for an exponential function, the rate of change of the voltage is proportional to the voltage, its instantaneous voltage. Then you will have an exponential envelope. But here the rate of change is always constant. You are injecting fixed packets, so it's always constant. So in that case it's going to be a linear function. So dV by dt, this is the amplitude variation I'm talking about, is proportional to some constant. It's always constant. So your V will be some k times t. Okay, so the amplitude is going to increase linearly. So this is a better approximation for a sinusoidal signal. So if I feed a sine wave, this is the way your output is going to look like. So the third and the final case is a case where I'm actually going to apply a sinusoid whose frequency is not equal to the resonant frequency of the system. So here I've shown here a pulse of time period which is half the pulse that we have analyzed in the previous problems. So here time period is t by 2. So frequency is going to be 2 omega naught. So for a pulse train, assuming the pulses to be very, very narrow, you can very easily show that, see, it's a pulse train with only positive pulses, so it's going to contain a DC content. So the spectral components, the frequency components are going to be 0, 2 omega naught, 4 omega naught, multiples of 2 omega naught, right? Its time period is t by 2. So the fundamental harmonic will be 2 omega naught, and it will contain all harmonics of 2 omega naught. So if you see, there is no energy at omega naught itself. And if I feed this as an input to this LC circuit, we will see what is the output that we are going to get. So here I have drawn the output here. So in the first half cycle you are going to feed a positive charge, so the voltage will be Q by C. At the end of the first half cycle, you are actually feeding a positive charge here. If you recall the previous example, we were feeding a negative charge. So the charge here is minus Q, and you are going to add a charge of plus Q at this point. The capacitor is going to absorb the plus Q charge, and suddenly it will come to 0. So then you should ask, okay, the capacitor had an energy stored in it. There was an energy because of the charge, okay, and it had an voltage across it. What happened to it? So that energy is dissipated by the current source. A current source, an ideal current source, can either dissipate or deliver energy. So in this case, the current source will dissipate all that energy. So the voltage waveform will come to 0 here. So at the end of the first cycle, again you're going to deliver a packet of charge, positive packet of charge, and it's going to oscillate for one half cycle, and then again it's going to remain 0 for the next half cycle. Okay, so now if you see, the output is bounded. I've applied a bounded input, the output is bounded. So that's what I've shown here. The output here is bounded. You have applied a finite input, and I'm getting the amplitude never blows up to infinity. But here you have to make a very, very important observation. The input signal had no energy content at omega naught. The terms it contained were 0, 2 omega naught, 4 omega naught, and harmonics of 2 omega naught. So there was no energy at omega naught. But if you look at the output here, the fundamental time period at the output is t. And we know that corresponds to a frequency of omega naught. So now we are actually, I'll do a intuitive analysis in a few moments. The energy content of the output signal is, it will actually have harmonics or energy at omega naught, 2 omega naught, 4 omega naught, and so on. So that's the interesting difference here. For any LTI system, whether it's a left of plane pole or right of plane pole system, the output frequency was sinusoidal. If the output contained a sinusoid, that was always equal to the input frequency. But for a resonant system, we are actually seeing the output frequencies, there are some additional frequencies at the output as well. So here, to generalize it, I fed an input of this type, omega x, to the system, frequency with omega x. The output actually has omega x frequencies, but it also has an additional frequency omega naught in it. And that is because of the resonant behavior of the system. So that resonant behavior is a natural response of the system. So to generalize this result, I'll use a similar way that we did in the previous problems. If I fed an input of this type, Vp cos omega xt to the system, the output is going to look like this, Vp dash into cos omega x plus phi. It will have a phase variable as well. And Vp dash is simply Vp into mod of h of j. In this case, it's going to be omega x. Okay. Now, omega x is not equal to omega naught. So therefore, this will be finite. Okay. So the fourth response is actually finite. But then the natural response, which is determined by the impulse response, is a sine wave. And that's going to be a sine wave at a frequency of omega naught. Okay, so that's why you will see an additional frequency in addition to the input frequency in a resonant system. Okay, so but the output is still bounded. So that's the important point here. The output, overall output, there will be a resonant term here, an additional frequency term here, which is not present in the input, but the output will be bounded still. If I go by an absolute definition of bounded input, bounded output stability criterion, then by that definition, this is a stable system. But generally, we won't call it as stable because you cannot have components which are of different frequency than that is desired. Okay, so this will be classified as an unstable system by analog engineers. So I'm just trying to make a point that even though it's bounded input, bounded output stability, we will still not consider this as a stable system. So the important point we saw for this system is that, okay, let me just complete one point. So here I said that the fundamental frequency, the frequency content of this signal, it's not very obvious. I said it's omega naught, 2 omega naught, and 4 omega naught. So I'll give a very simple and intuitive derivation for that result, and then come back and make some comments on this, the frequency response of resonant systems. So we need to find the spectral content of this signal. So which is nothing but it's half sine wave, and for the other cycle it is 0. Half cycle it is 0, and it's a sine wave for one half cycle. So you can generate that signal by two well-known signals. One is a sine wave, which Fourier transform is going to be just an impulse at omega naught. And I'll multiply that with a pulse train, a pulse signal, a square wave signal with 50% duty cycle. It's going to take two values, which is 0 and 1. Okay, so this is an odd symmetric 50% duty cycle function. So therefore, since it's going to go between 0 and 1, it will have a finite DC content. So that's why you'll have an impulse at DC. This is the Fourier transform. I'm showing here the Fourier transform of the signal. And it will contain energy only at the odd harmonics of the fundamental frequency, which is omega naught here, which is 2 pi by t. Okay, so this is an odd symmetric function. So therefore, it will only contain odd harmonics. Now the harmonics power will actually reduce as you increase in frequency. Again, this is a very standard result for a 50% duty cycle signal. It will only contain odd harmonics, and you can find it in any textbook. So using these two, we will try to derive the frequency content of this signal. So if I multiply this with this, if I multiply the pulse signal which goes from 0 to 1 with this sinusoidal signal, I will get this signal. So multiplication in time domain, in frequency domain it is convolution. So I have to convolve this signal with this signal. So I have only shown the energy at positive frequencies. So if I convolve this with this, it just amounts to shifting this whole graph by omega naught in this direction, and the negative frequencies will also be shifted by omega naught in this direction. So this will become omega naught, this will become 2, 4, 6 and so on. So you will see omega naught, 2 omega naught, 4 omega naught and 6 omega naught and so on. Okay, the energy will decay like this. And similarly, this is for negative, I have shown it here for negative frequencies. So it makes sense, you can see that there is no DC content in the signal. Okay, and you have energy at omega naught and omega naught as well, in addition to 2, 4 and all that. The input signal, if you see, contain energy only at 2, 4 and 0, 2, 4 and so on. But this signal actually has energy at omega naught as well. Okay, so I have just given a simple intuitive proof for this result. So the important point we discussed here is that, I'll just come back to this point now. The important point we discussed here is that for a resonant system, if the response of a resonant system to an input which starts at t equal to 0 is going to contain a forced response component and a natural response component. The natural response component will contain a frequency omega naught. Okay, so that's why you will see a frequency other than the input frequency only for an resonant systems, even though it's an LTI system, but you will see for that. And again, it's a bounded output, bounded input. The outputs are bounded, but I mean, by going by the strict definition of a bounded input, bounded output system, the system can be called as a stable system for this input. But for specific inputs, when your input happens to be omega naught itself, the system becomes an unstable system. So again, this will be a marginally stable system. Okay, for some systems, for some inputs, the system behaves as an unstable system. The output just grows unbounded. And that is obvious from frequency response because the gain of the system is infinity, and even from the analysis that we did so far. Okay, and I haven't discussed the system with complex poles. That is same as the right of plane pole and left of plane pole systems. So you will have forced response and you will also have a natural response. So you can very easily say that for a left of plane pole system, natural response will go down to 0, and the forced response is something that can be easily calculated from the initial discussions, the initial analysis that we did in this lecture. In the next lecture, I'll probably give a rigorous proof of some of the results that I've discussed now, and we'll very quickly move on to the frequency response of single stage amplifiers.